Hello, and welcome to the Additive Manufacturing Research Opportunities webinar, hosted by the Army HBCU-MI Student Program for Army Research and Knowledge, or SPARK. Today's webinar focuses on the exciting field of additive manufacturing, referred to as AM for short, a transformative technology more commonly known as 3D printing. We are pleased to offer a closer look at how this innovation is shaping the future of defense applications and research collaboration opportunities with the Army. We are honored to have Dr. Nicholas Koo and Dr. Jihan Yu as today's featured speakers from the DEVCOM Army Research Laboratory. Dr. Yu serves as the Convergent Manufacturing Team Leader. Together, they will provide an overview of AM's progression from rapid prototyping to cutting-edge defense applications. They will also share insights into ARL's current research, including the development of tailored metallic alloys and energetic materials, and discuss how academic researchers can engage with ARL through broad agency announcements and other collaborative mechanisms. My name is Crystal Nolan, and before we begin, I'd like to briefly go over the webinar format. Please keep your microphone muted during the presentation. However, during the Q&A session, you will be invited to unmute and ask questions. Alternatively, you can submit questions at any time via the chat, and we will compile them for the speakers to address during the Q&A. If you have questions about using the Zoom platform for this event, please feel free to enter them in the chat window now. Technical support is on hand to help you with any issues you may be having. Finally, within the next few weeks, we will send a link to the webinar recording to everyone who registered. This will allow you to revisit key parts of the presentation and Q&A, or share it with colleagues who may find it valuable. And with that, I'll turn it over to our DEVCOM ARL Army Research Office speakers.
Thank you, Crystal. Let me share the screen.
Fantastic. Your screen looks fantastic.
Okay, thank you.
You're welcome.
Good afternoon, everyone. Thank you for joining us for this seminar. I am Dr. Jan Yu, and my colleague is Dr. Nick Koo. So I will start with the first half of the seminar on additive manufacturing. Disclaimer. So the view expressed by us, the authors, are our own and may not reflect the official policy or the position of the Department of the Army, Department of Defense, or the U.S. government. So here's our presentation outline. We're just going to give a brief introduction to our organization, the DEVCOM Army Research Laboratory, and give you a fun little history about additive manufacturing. Then we go into what types of research on additive manufacturing we have been performing at DEVCOM ARL, and then followed by a question and answer. So here's the map showing our location. So our headquarters at Adelphi, Maryland, and our laboratory location is at Aberdeen Proving Ground. And also we have satellite sites all over the country. We call what we call regional sites, and they are co-located at university. Within ARL, we have 11 competency or divisions. What we mean by competency is that we are kind of align our focus research on the Army application, military application. So where I and Dr. Koo are located is within the Science of Extreme Material Division. So that's dealing with all the materials and process in terms of military materials. So we are the Foundational Research Institute. So we're dealing with 6.1 and 6.2 fundamental research. All right, here's a fun history on additive manufacturing. Actually, this concept started long time ago. It's about almost a century. You can see that at the timeline beginning in 1860s, where photography become very advanced at that time, and then people start to use photograph to reconstruct 3D images just by using photosensitive gels or silver back then, silver gels. And then they have this concept of building up a structure layer by layer for topographic maps. You can see, and then later on in the 50s, the first patent was filed on what resemble the first 3D printer. You can see it has a roller that spread the in this case it's a sand mold, a spread layer of material, and you additively build up layer by layer. So that's the concept. And then it came, and then later became the a concept of stereolithography. That's SLA, and that's where the file name came from. STL file. It's called stereolithography file, and that will enable you to build three-dimensional objects, right? And then later on, you have the powder selective sintering method, and then you have the fused filament deposition model, or FFF or FDM, and that become very popular recently because its original patent has been expired. So now we have so many different company and startup to invest in FDM printer for the masses commercialization. So you can see additive manufacturing went through quite a revolution, since the 1850s. And here I show you that some fun fact on about additive manufacturing, why we do it, and I can highlight all these key phrases or keywords from a patent that was filed in 1864. You can see that it's the same word that we have been using to justify why we want to do additive manufacturing, right? Greater rapidity, less cost, right? Less than the time necessary for the production, right? You can scale a larger or smaller dimension, right? Any proportion desired. All this, the advantage of using additive manufacturing. So the example I show here is a full body 3D body scanning device. Back in the 1860s, uh, it takes a whole building for you to reconstruct a 3D dimensional body. Now we just need a small room to scan the whole body, and then actually we can print the scan as well. So this is a old concept, but now we can do it readily and quickly So that's a fun fact. And now refer back this what they call a layer by layer additive, right? So in the past, there's a lot of demand for topographical maps for the military. So one way to reconstruct the topographical map is that slice by slice reconstruction. So this is exactly what they did in the past. So this is a concept for additive manufacturing, for, layer by layer. And then recently, of course, we have some of the uh, machine that was obsolete um, by now, but it was state of art back in the 80s and 90s. And one more important pattern here is the stereolithography, right? So now it become, everyone know what the STL file is, that's where it came from. It's the stereolithography technique for building layer by layer using a photosensitive resin. And of course, it's the 3D system that make this technology widely available. And then, of course, selective sintering, led by a group of inventor at the University of Texas, Austin. And it's in the late 80s. And then that's what kicks off the renewed interest in 3D printing or additive manufacturing. And of course, FDM modeling, 1992 patent, and that later on became a Stratasys system. And this actually popularized 3D printing technologies. All right, now let's switch gear a little bit to share with everyone about what the Army Research Laboratory is doing in terms of additive manufacturing research. So we are an organization that focus on feedstock development for additive manufacturing. That's including high strength steel, aluminum, magnesium, right, refractory metal. And Nick Coogan, he's gonna go over his field of research, which is in ceramic additive manufacturing. But we deal with the same thing, the feedstock development, the modeling, the simulation, and the digital tool pathing, as well as the in situ monitoring, and all that feed into expeditionary manufacturing. That is to say, we want to manufacture parts in the field at the point of need, so we can repair the parts quickly, so we don't have to waste time to wait for the parts to ship overseas, or we can use indigenous material or recycled material to rebuild the part. So this is kind of a high level concept that we want to do, or we will try to collaborate, or we try to advance the art of 3D additive manufacturing. So in particular, we have a program in researching powder bed fusion process. So you can see in this graph that additive manufacturing is a very complex process, because you're dealing with multi-phase material, very complex phase transition, as well as the thermodynamic and kinetics. So all this create a huge challenge in terms of get a full understanding of additive manufacturing. So I just give it share the example of what we try to go after, like what kind of experiment we are working on, what kind of in situ monitoring sense that we're working on, and what kind of process aspect we're working on. So one example on the point of need manufacturing is that we want to recycle steels, what we call battlefield scrap steel in the field. So we do have a lot of scrap in the field. We want to turn that scrap into a powder and then print useful part of it. So it's more of a cycle, recycling battlefield scrap into a useful part. That's one main, very very focus item right now. Machine learning. That's the latest uh, addition to our research portfolio, because the advance of machine learning algorithms have been advanced so much that we have to incorporate this for the analysis of our the complexity of additive manufacturing process. And also we want use machine learning to enable us to quantify additive manufacture part. So here's some of the example I show about layer by layer using machine learning to predict APR, the thermal history, and how the microstructure evolve and detect any kind of anomaly, so that we know whether the part qualify or disqualify for usage. So that's one example of what we the application of machine learning with additive manufacturing. Here's the example of what the Army has failed in Afghanistan and other parts around the world. We try to demonstrate expeditionary manufacturing. That's to say, we want to manufacture useful parts at the point of need, close where the soldiers are deployed. So here's some of the example we've been doing with this X Lab. Another area we focus on is printed electronics. So some of the there's a lot of Army platform that is what we call a legacy system. The original manufacturer, they no longer manufacture them, but the Army still need the system to carry out the mission. So usually we couldn't even find the original joint or the or any of the parts. So here we demonstrate we can reverse engineer a electrical part that we can print and populate with the functional devices, and has a replacement. So here's one example of a research project we've done. So with that, I would let Nick Koo to talk more about his ceramic interest. So at the end, I will come back and talk about collaborative research and ideas, and how where to contact us. Okay.
Thanks, Jan.
Okay. Go ahead.
Give me 1 second, and I will share my screen. Are you guys able to see that okay?
Yeah.
All right, awesome. Yep. So Jan gave a really good overview on sort of our strategic research objectives towards additive manufacturing. I'm going to get more, I guess, a bit more specific and talk specifically about what we're working on in the area of ceramic materials and additive manufacturing. So, as Jan said, I'm Nicholas Koo. I'm a materials engineer here at the Army Research Lab, based in Aberdeen Proving Ground, Maryland. So, yeah, I guess this is kind of, our idea on how we're going to look at additive manufacturing for ceramics, right? It's much more of a materials development research area. We're not really looking at sort of
Hey, Nick, I think you have the wrong screen. We only see the preview, not the full.
Okay. Is that coming up as full or just preview?
Just okay.
Let me try this.
Yeah.
Sorry, everybody. Is that up? And you're seeing
that helps. Yeah. Okay, awesome. That's good.
Okay. Yep. So additive manufacturing as an enabler. So, in terms of ceramic processing 101, a lot of it is a powder-based solid state sintering process, right? Where you're utilizing extremely high temperature and high pressure in order to form parts. Advanced ceramic materials. And generally, you're stuck because you're using uniaxial pressure and things like hot pressing. Monolithic compositions, very simple geometries, right? So what we want to look at is, can we use additive manufacturing in order to enable complex geometries or complex compositions across our parts, right? So we're not within our ceramics branch. I sit in a different branch here at ARL than Dr. Yu, but what I would say is, we're not generally mechanical. We're generally materials engineers here. We're not mechanical engineers. We're not developing new AM technologies. We're not developing new tool paths. We're trying to really use the AM technologies out there, and how can we apply ceramic materials, and what can it do to our ceramic materials processing. Not that we're not interested in that. It's definitely areas of collaboration, but in terms of the expertise that we have in-house, this is what we're concentrating on. So, Jan gave a really good overview of the different AM methods and the history of AM. But, just to give you an overview, these are from ASTM, the 7 families of AM, additive manufacturing. I'm going to concentrate on these 4 in vat polymerization, binder jetting, material extrusion, and directed energy deposition. Of course, not in this order, but I'm going to start with material extrusion. So basically, that's on-demand material extrusion, on-demand sort of material deposition, right? So this kind of work started about 5-6 years ago, and we didn't find a multi-material ceramic printer on the market at that time, commercially available off the shelf. So we actually built our own, where we took a Lulzbot TAS6, an off-the-shelf FDM printer, cannibalized it to make an XYZ control gantry, and then actually created this feed system where we can load our ceramic slurries or paste, think a clay-like material with the consistency of like toothpaste, into those syringes that you can see up on top. And then those 2 stepper motors up above them would actually volumetrically deliver material down through those tubes into that singular print head. You can see that print head exploded on the right-hand side, expanded. And what happens is you'll have 2 materials entering the same barrel, and we have a 3rd stepper motor actually spinning a auger that helps provide conveyance, but also inline mixing. So now we have in situ composition control, right? Now, depending on how we deliver, what ratio we deliver it down through the feed system, we could print all material A, all material B, or any combination of the 2 as we move through the print. So being a direct ink writer, material extrusion type AM process, we do a lot of feedstock development and understanding the rheological behavior. Definitely a big area of research and collaboration that we can work further on. We're concentrating mainly on particulate suspensions. So we're taking powder, water, some organic binder, and creating sort of a slurry-based material, generally about 50% solids loading by volume, but understanding the binder, what kind of solvent is being used, or even going to different material, non-powder-based feedstocks like pre-ceramic polymers are all of interest, but sort of outside of what we're concentrating on in-house here at ARL. And then really understand the rheological properties of these, right? Because if you have something that's too thick, too viscous, it won't extrude through your nozzle. But also, if you have something that's too fluid, it will flow out, but then it won't retain its shape after you deposit it down on the bed. So understanding that rheological role, or that flow role of your feedstock, is extremely important. So these are just some of the simple schematics of some of the parts that we've created, different parts, right? So we have monolithic materials, just to really understand how the AM process is changing our bulk material properties. And these are all carbide-based ceramics, so mainly boron carbide and silicon carbide. You can see on that second column the continuous route. So that's we're utilizing that composition change in situ during this print. So
excuse me,
yes,
the screen doesn't show.
Are you guys seeing ceramic design through DIY?
Yes. I'm seeing your screen clearly.
Okay.
How about your face? Yes, face.
There is a pop-up there. Could you hide it some?
Sorry. Is that Are we good, or am I?
Yeah, it's all good now.
Okay, sorry about that. So this second column, continuous, basically what we did was we started with full boron carbide, and we were actually able to change the composition as we built the part. 10% volume change in composition each layer until we got to full silicon carbide to create sort of a functional grading. And then we also created these sort of discrete layers. The idea behind this was mainly for soldier protection. The idea was in advanced ceramics, can we influence crack propagation through a material through changing composition? So this is that same functionally graded part that I showed in that second column in the previous slide. But this is after we sintered it, we sliced it in half, and then you could see that cross section through SEM imaging. So the darker material will be the boron carbide, the brighter material will be silicon carbide. So you can begin to see how that composition changes. Our mixing isn't bad, but not great, right? If you remember from the printer, we had a simple auger design, and it's generally about a 2-inch mixing area, right? That auger is only about 2 inches in length. So I would say there's a lot of work and design that could be done in order to increase that mixing, or whether it's changing the auger design or changing the mixer itself. But we are getting these large clumps of one material in the other, right? But that's kind of where we're at right now. And then in terms of the discrete sort of different layered materials, residual stress is a big one, right? So whenever you're trying to thermally process two different materials that have different coefficient of thermal expansion, right, you would build up some sort of residual thermal stresses. So you can see that here on that top left, we see a crack sort of emanating through the boron carbide region and then bifurcating and terminating in the silicon carbide region, right? So from the difference of thermal expansion, I will tell you that when you cool these two materials down, your boron carbide would be in tension, which is why you see the crack running through it. And then in the silicon carbide region, it would be in compression. So that's kind of showing that that compressive layer is actually affecting that crack propagation and mitigating it, right? So maybe that's something that we can engineer and use. But how do we actually characterize that? So in the upper right-hand box, you can see how we're using Raman spectroscopy, so an IR-based spectroscopy, to measure this residual stress as we scan through our parts. And then on the bottom, we're doing some analytical calculations just to calculate out what we expect the residual stress to be in these different composition regions given the temperatures that we process it at. So just to kind of understand mechanical properties, this is kind of a qualitative image, but I think it shows it pretty well, where this is a flexural bar that we broke in half, and then the two ends are actually facing towards you. So that fracture surface, the fracture origin is actually along the center, and these are mirrors of the two ends of the fracture surface. But what you can see there is, where it fractures, you kind of get this pretty clean fracture region, but on the back end of the bar during flexural, when it failed, you can begin to see the sort of wavy pattern, and that seems to correlate pretty well with the different layer thicknesses. So something about that residual stress is affecting the way the crack propagates through the material. Changing topics from material extrusion to binder jetting. Binder jetting is a 3D manufacturing, an additive manufacturing technique where you're taking dry powder and basically you have a dry powder bed. You use a print head, not unlike what's in your copy machine, your Xerox machine, and that drops liquid droplets of liquid binder to locally glue your powder together, and then another layer of dry powder is placed on top. So as any additive manufacturing, any good 3D printing research group, we have the we printed our logo. There's the AFC logo on the right-hand side out of silicon carbide. The problem is that generally, because it's a dry powder process, you have two competing mechanisms, right? You want something that's really, really flowable. So the material packs really well in your powder bed by itself, and it will flow out of that hopper during printing. So you want pretty coarse powder feedstocks for good prints. On the other hand, 90% of the time when we're doing ceramics research, we concentrate on solid state sintering to densify these materials. And that's a surface area driven effect, right? So we want extremely fine powder feedstocks to allow for solid state sintering. So generally, well-behaving feedstocks for binder jetting, for actual printing, for forming, are very difficult to sinter. So that previous part that I showed, that silicon carbide AFC logo on the previous slide, we were able to print that, but the particle size was so large it would not sinter. So one of the areas of research that we're heavily investing in right now in the area of binder jetting is what we call polymer infiltration and pyrolysis, so a PIP process. Basically, you would create a powder preformed through binder jet. We're infiltrating this with a pre-ceramic polymer, so a silicon-based polymer that when we pyrolyze will form silicon carbide. So you could see through the progression, basically you infiltrate it with the resin, you pyrolyze that, it opens up pores and cracks, then you re-infiltrate all those pores and cracks with more resin, and so on and so forth. It's a cyclic process until you fully densify your part. And this kind of shows that here, right? So we looked at three, in the red, blue, and purple, we looked at 3 different silicon carbide feedstocks. We printed parts, and then we began to do through 2 cycles of infiltration and pyrolysis. And what you can see is the particle size distribution of feedstock affects the print, but it also affects the density of the print. And it also affects, because you're then getting different pore sizes, how it infiltrates and how it pyrolyzes, right? So this is definitely an area of interest for us, not only in terms of chemistry of the pre-ceramic polymer that we're infiltrating with, but also viscosity, because that affects how it infiltrates, but also, and then also the particle size distribution and printability of the powder itself. Switching gears again, so directed energy deposition is an area that we're pretty interested in. So this is a AM technique where you're basically spraying powder at a laser, and then almost like spot welding material. You create a pseudo melt pool at the point where you're spraying your powder, where the laser beam's hitting. You can see a schematic of that on the upper left. Primarily used with metals, and we're trying to enable it with ceramics. And what I would say is normally ceramics have much higher melting temperature than metals, which makes it very difficult to laser process. So in order to enable any sort of laser-based additive manufacturing for ceramics, the first thing we have to do is understand how ceramics can be processed with lasers, right? So that's a really big area of interest that we have right now. And one of the things that we're trying to figure out is how ceramic materials potentially react under a laser system. So in this project that I'm going to talk about, we were actually looking at using precursors in titanium and boron, and under a laser reacted to form titanium diboride, an advanced ceramic that we have some interest in. So we did a lot of work on understanding how well you need to mix the titanium and boron in micron up to down to nanoscale different powders, different mixing intensities, and then looked at different laser parameters to see how it affected both the density of the part, how the phases formed, the microstructure, and things like that. But laser-based processing is definitely an area of interest, because that would open up many different techniques on laser-based additive manufacturing for ceramics. Finally, I'm going to talk very quickly about that photopolymerization additive manufacturing. So in this case, basically you have a UV curable resin that you're suspending your ceramic powder in, and then curing each layer by layer in order to form your part. The advantage is extremely high resolution, right? Because you do have your light sources is your controlling your geometric complexity. But really where we're at right now here in stereolithography or dynamic light processing is creating these slurries, right? We're taking the commercial powders that we have interest in and then suspending those in different acrylate-based resins and trying to understand how does that allow for curing of this material, right? So currently what we're doing is we kind of have a tape casting set up in order to create thin layers of this slurry and then using a UV lamp in order to understand how deep it can cure, right? So the more powder you put in, the higher the solids loading, the better it will sinter, but the more it's going to scatter and reduce your depth of cure in your material, right? So you're playing with that sort of balance. And then also the material itself, right? We have, in our previous work, we're much more interested in sort of carbides and borides. These are relatively dark powders with high refractive indexes. We spent a lot of time spinning our wheels trying to figure out if we can get any sort of appreciable depth of cure, but because of just how much these scatter and absorb the light source, you can't really do high refractive index materials using this AM process, right? So we're really left with, you know, the white powders, oxide powders I showed here on this slide, alumina, which could definitely have some applications in transparent materials or RF kind of based materials, so dielectrics, which is where we're kind of targeting this technology here. So in summary, you know, I moved really quickly, but I wanted to make sure we had time for a Q&A afterwards. You know, we've been doing in terms of ceramic additive manufacturing.
Hi, how are you?
Yeah, I'm good. I received your email.
We've been
Yeah.
we've been looking.
Okay,
Someone's
I'll
got a
buy
hot mic on.
business edition. I'll buy. And then
Yes, that's what it appears.
also I have a limited
there's-
budget and time. The budget is
Okay,
the
Miss Moon,
3,200 or
maybe for someone from the tech team
300.
can mute
So
the person
you
that's speaking. Okay, wonderful. And you can
Okay.
continue.
Yeah. So you know, just to end and summarize, right? So in different terms of ceramic additive manufacturing research, we're looking at the area of direct ink write, where we're have a lot of work on rheological development of the actual feedstocks of the suspensions. We're looking at binder jetting, where we have a lot of interest, primarily in polymer infiltration and pyrolysis, right? So understanding pre-ceramic polymer chemistry and how that can infiltrate and densify, help us densify these materials. In terms of directed energy deposition, a lot of it's just how do lasers interact with these ceramic materials. And then finally, in terms of that polymerization, formulating UV curable suspensions, both on the resin side, but also understanding how the particle size and particle size distribution can affect that. So with that, my email's on the bottom, but I'm also going to just quickly bring up this slide. So sort of some ideas on how we can work together. So this is, you know, a Spark hosted webinar. Spark has been a great program that we've utilized here at ARL for bringing in students as well as collaborators. There is a active broad agency announcement. There is the topic ID there on the right-hand side. So this is the Advanced Manufacturing Research in Support of the Science of Extreme Materials Competency. I listed the link there. That'll bring you to the general ARL BAA site, and then you could search that topic ID in order to find that that specific announcement and some details on it as well. Outside of Spark, especially for students in the blue, green, and purple, I've listed some other internship and funding opportunities. What I will say is, you know, those are a bit more competitive than Spark, not in terms of prestige, but what I would say just in terms of funding amount and the community that it's opened up to. You know, being that you guys in Spark or HBCU-MI institutions, you have you are eligible for Spark where many of the others are not. And then what I would say is, in terms of fellowships, if you're a grad student looking for or faculty looking for grad student funding opportunities, there's SMART, NDSEG, and NRC, where we work as sort of mentors for the student through their fellowship program. And then just kind of some closing links on that bottom left. You can see the DEVCOM ARL homepage, a link to the Army modernization priorities, where all of our research kind of links back to, and then the technical reports at DTIC. A lot of the reports that I've referenced in this presentation, you could find through there. So with that, Crystal, I guess I'll hand it back to you in order to facilitate the Q&A.
Thank you so much. What informative presentations. We really appreciate that. So again, I want to thank you, Dr. Koo and Dr. Yu. And yes, at this time, we would like to open the floor for questions. So there's one of two ways you can do it. You can feel free to open your mic at this time, and you can direct your question to the speaker of your choice. Or you can also type in your question in the chat pod. And when things slow down, I'll jump over to the chat pod and ask any questions that are there. So with that being said, who would like to ask the first question?
Yeah, I saw a question in the chat already from Francis. So I can answer that. Is this a grant solicitation for students only, or for faculty, or for both? So I can go into detail a little bit, and then share a window so that you can share the links. Let's see. Okay. All right. So the opportunity that Dr. Koo mentioned is the Army Educational Outreach Program. So this is a particularly program is for students from anywhere from high school up through a graduate student, as well as educated high school educators and teachers. So this is the Army Education Outreach Program. Usually it takes place in the summertime. Next, I'm going to show this is called the National Defense Science and Engineering Graduate Fellowship Program. So this program is for second-year graduate students and up. So this is a competitive fellowship program, fully paid stipend, as well as a tuition for graduate study.
Wonderful.
And lastly, is the SMART program, the Science Mathematics Research for Transformation. It's a DoD scholarship for both undergraduate and graduate. A graduating senior in high school can start the application process, as well as the first year of undergrad and first year of graduate students. And it's very competitive because at the end of the fellowship, upon successful graduation, the person will have 3 years of obligation to do research at our laboratory, at any of the DoD laboratory. So that's the difference between SMART and the other fellowships. And lastly, Nick Koo mentioned about the BA announcement. So this is the link and website to the our board and agency announcement, and where you can browse the current topic of interest. And we just came from, we are just from the material division. Remember that there's 11 other division that focus on sciences. So you can then select what your interests are, and you can contact the what they call a technical POC, which is, have an email and contact. And you can see some of the closing date and opening date as well. So you can look through it. If you find something that you're interested in collaboration with us, you can send maybe an email or a white paper if you have it ready. So you can introduce, the idea, what particular field of research that you're interested in. So, yeah. So yeah, that's what I have.
Wonderful.
Yep.
Thank you, Dr. Yu, for walking us through those opportunities and showing those websites. I'm quite sure that is very impactful for those who are interested in those activities. Is there anyone who has a question now that would like to unmute, or we can?
I have a question. This is Jay Mishra from New Mexico State University, if I may.
Sure, absolutely.
Thank you very much. Thank you again for all the presentations. It was really informative. A question I had was, which I put in the chat too, is there an interest in enabling technologies such as, if you're looking at using artificial intelligence, machine learning, cybersecurity, networking support, etc., in the context of manufacturing at scale, distributed manufacturing, bringing more manufacturing online by doing it remotely. I know this is the materials division, but is there such an interest? And if so, who should we talk to?
Yeah, so some of your ideas fell under the cybersecurity aspect, the computer sciences and data informatics. So it could be some cross competency lead, but
Right.
in particular, when you mentioned cybersecurity and network support to enable distributed whatever, whether it's manufacturing or data package, that will fall under, most likely will be the computer science and data sciences.
Thank you.
And there are opportunity out there, yes.
Thank you very much.
And I think Sentosh also asked the same question, can you provide opportunity for computational material area? So most likely it would be in the mathematics or the mechanical sciences. Yes, there's opportunity. So there are many. I mean, when I show the website, I can show the website again. Let me just quickly do that. Let's see. Right. Okay. Everyone see this, right? Yeah. So you can see, there's maybe over 100, 82, at least 82 opportunity core on various field of study. So yes, I think you were able to find at least one or two that might align with your interests. So yeah, and the website's here, so I can copy and paste onto the chat.
Thank you, Dr. Yu. Yes. Wonderful. I see that someone would like to know if we're going to share the presentation. That presentation will be shared with everyone who is registered in just a few weeks. So we have your email. You will receive a link to that to today's presentation shortly. Anyone else have a question they want to unmute their microphone and ask?
Yeah, if I can ask a question, it's Andre Voivodin, I'm University of North Texas, get my camera here. So I had a question. Is there interest also in developing methods for in situ monitoring of either alloy or ceramic processing? And is this in the scope of your group particular interest, or is it maybe there some processing groups? And I'm talking about different methods from defect mapping to compositional monitoring.
Jen, did you want to take this one, or?
Yeah. So there's always interest in terms of in situ monitoring. In particular, we're looking for more of a right now. In my area, in particular, is we want to record the thermal history when we're doing like powder bed fusion or directed energy deposition. We always want a very good a sensor that give us a true temperature, the actual temperature of the thermal history profile. So, Nick, anything to add?
Yeah, I would say this is I think ceramics are lagging a bit behind, especially in terms of metals, into understanding this. But one of sort of the reach goals is really not only being able to monitor the process, but actually be able to link those to the final defects or final strength of the material, right? So basically, if you kind of fall out of that parameter space, could you almost abandon that part and reduce kind of waste time, right? So understanding that and understanding not only just in situ processing, but the linkage to the final part properties is definitely of interest.
Yeah, because some of the methods you showed, particularly direct energy deposition methods, and maybe some other way you talked about distilling material processing and gradients. You may also want to know in real time how the gradients comes up in terms of not only the defects, but also the composition itself, because many things can go wrong, right, so to speak, from powder delivery to the sintering. So you want to compensate it in real time, otherwise, your parts will be kind of waste. So I'm asking it because I'm in the UNT here. We have a center in additive manufacturing, and one of the areas that we're pushing strongly for this in situ instrumentation with hopefully in real time getting some of the feedback and correction. I'm happy to connect, actually more on that and provide some information. Maybe send some papers we published.
Yeah, that would be great. Especially in the area of directing, right? I see a lot of groups looking at just optical imaging, like putting a webcam in and doing something like that. The issue that I have with that is, it does allow you to sort of know when you have a print defect where you can scrap the part, but it doesn't allow you to sort of correct in real time. I've seen some groups kind of begin to put pressure transducers in the nozzle to try to get an idea on, rheological properties of the thing as it's printing. And I feel like that could be interesting with the idea that, if you can detect a clog coming before it comes, maybe you can kind of stop the print and clear away the nozzle before you continue to save a part.
Exactly.
Yeah.
I don't know, Nicholas, if it's possible to share your email.
Yeah, I will put that in the chat right now.
Yeah, that may you continue. I don't want to take the time from other people may ask questions.
Thank you. Great question though.
Do we have another question? Would someone like to unmute? I do see that there are several questions. Did I hear someone?
Okay, I got a question from Ismail
Okay.
about the research in civil engineering and construction engineering. Not us, not DEVCOM Army Research Laboratory. So we're dealing with 6162 research. We're not dealing with civil and construction. The Army Corps of Engineering is dealing with civil and construction of using additive manufacturing. Yes, they have a huge program in concrete building barracks. So this is under ERDAC. It's called the Engineering Research Science, I think, Directory. So yes, it's the Army Corps of Engineering.
Thank you for that, Dr. Yu.
Yeah.
Yes. Let's see. We have what other questions do we have here in the chat that haven't been answered?
Yeah, I saw one here too. Can
Okay.
you provide opportunity for digital twin in additive manufacturing area? So digital twin right now it is a challenging problem, like to create an additive manufacturing twin, because right now we just a lack of the in situ monitoring, like obtaining the thermal histories, mainly how the heat evolve. That's in the case of laser bed powder fusion as well as e-beam or e-beam fusion and DED. So I think to get to the point where we can deploy digital twinning is that we would have to solve the in situ monitoring situation in terms of the thermal history.
Okay. Thank you again for that.
No problem. And I'm just
Yes.
scrolling through see what other
Yeah,
question.
that's right.
Okay. Yeah, yes, let's see.
If I may ask a question.
Mm-hmm.
Hey, this is Ben Zhu from University of Houston. So, very interesting talk, and I just have a quick question regarding the additive manufacturing for some special alloy, for example, for high temperature applications. So, does a ARL is very interested about some technical alloy, for high temperature applications. Input. Can you give some comments regarding the temperature range, also any special interests for like a corrosion or some other material related properties that we can focus on, so we can use the additive manufacturing process to kind of tackle those issues?
Sure, yeah. So in the high temperature material, we interested in refractory metals, any kind of a high what they call a high entropy alloys. So we're looking for a surface temperature, 1,000 degrees and above. So that's our current field of interest. Do I answer that question?
Yes, thank you.
Okay.
Yeah. We actually did some of the study, using some mechanical alloy powders for 3D printing. Already have some published papers, and we'll also try to, because basically, I'm doing a lot of research for solar thermal, which is concentrated solar power. Our temperature range from 800 to 1,000. So I'm thinking about maybe that could be an opportunity to push the limit about 1,000 for some other DOE applications.
Certainly, thank you.
Yeah,
All right.
I'll share some of published papers and with you and Nick. Thanks.
Yeah, sure thing. Yeah, I have a question from Santari. Okay, do you have an interest in develop suitable polymer binder? So Nick, that's probably for you.
Yeah. I was just gonna talk about that, but yes, we definitely do. Here in the ceramics branch, we are mainly ceramists. So my organic chemistry background is pretty poor. So what I would say is we've been using commercial off-the-shelf polymer binders in order to create our suspensions for direct ink right. In terms of binder jetting, we have an X1 binder jet. We've been using what they commercially provide as binder systems, but fine-tuning the binder chemistries, the polymer chemistries to increase green strength, increase dispersion, definitely, or tune rheology. That's definitely something we're of interest. Also, we're looking at carbides and borides, and a lot of the time, a carbon source is needed as a sintering aid. So actually being able to use and tune the chemistry to really get the char yield we want is something that we've always kind of had an interest in, but we've never really had the chemistry background in order to kind of that's another area of interest, kind of the idea of tuning binder chemistry to kind of give us the sintering aids that we would want in our ceramic processing as well. So just kind of food for thought.
Thank you. Yeah, so our research group, we mostly work with photothermal nanomaterials in polymer, and then we do the direct ink writing with it, so that we can get the structure. And by the way, I'm Sanchari Chaudhary. I'm from New Mexico Tech. Sorry, I forgot to introduce myself. So in our group, we do have a polymer scientist who we collaborate with. And I'm actually a photothermal nanomaterials person, but I do have a very strong collaboration with a theoretician too, who actually does the calculation of heat transfer and stuff like that, right? Like which will be important for when you are trying to do the charting and stuff like that. So we do have lots of expertise in dispersion. Like one of the problem you talked about, a lot of expertise on dispersion, a lot of expertise on the polymer, which will match the nanoparticle so that you can disperse it better. So we have a lot of expertise on that part.
Yeah, that would be great. Suspension development and formulation is definitely one that we spend a lot of time on, that we would perhaps like a bit more basic fundamental knowledge in order to kind of reduce sort of the amount of the test matrix that we usually start with, right? Or increasing, getting a better polymer off the bat. One thing that I would also say is any binder we put in, we do need to burn back out, and understanding debinding in terms of polymer pyrrolization and how that gases kind of escapes from these powder networks. That's also definitely an area of interest as well.
Wow. So Dr. Koo and Dr. Yu, I do want to step in right now about this time. We have to wrap it up. But I want to thank you all for such engaging content. And I also would like to thank everyone that has attended today's webinar. And as I said, we do have to wrap up the Q&A session right now. However, you'll see the contact information for our speakers on your screen. Please feel free to take a photo so that you are able to follow up with Dr. Koo and Dr. Yu with any additional questions or discussions after the webinar has ended. Once again, we really would like to extend our gratitude to Dr. Nicholas Koo and Dr. Jihan Yu from the DEVCOM Army Research Office for sharing their insights. And of course, again, thanks to all of you joining us today to explore materials by design research opportunities with the Army. This concludes our presentation, and we sincerely hope that you have a great rest of your day. Goodbye.
Thanks, Crystal, for hosting.